So the implementation of the analog functions will require the use of amplifying devices, transistors. Then we need to understand how each transistor impacts the performance or introduces how much error introduces in our circuit. And then we have that most of the transistors that we saw in the previous schematic are there to provide DC biasing. Okay, so we have that those ones provide DC biasing, that it is to give power to the transistors that are forming the signal path. And all these transistors that are used for the biasing, the design of all the circuits around them, it is totally different than the one that is for the signal path. So we deal with these two problems as if they were orthogonal, so separate problems in different steps during the design. For the transistors that are part of the signal path, we have to take them separately. We need to be very careful with their noise performance because they contribute directly to the noise. They process the signal with the noise. Their speed or bandwidth, the nonlinear behavior, because they will introduce also nonlinearities. And something also that is very interesting is that there are no devices that are equal. So during fabrications, they face different conditions, and then they are slightly different. Not only that, they are also temperature dependent, so we will have to take in consideration these situations. So if we come back to the structured design that we are going to use, we are going to take in consideration these three main details. First, the noise. So some part of the circuit will contribute to noise to the system. We are going to focus on that part. Then another part of the circuit will contribute more with linearity. We're going to focus that part separately. Then we have that the bandwidth needs to be accomplished. We have to make sure that there is enough bandwidth and the circuit is stable, and also that it is able to handle very quick variations at the input. And finally, when we have found all the alternatives or solutions, we will select one for the implementation of the biasing. So we handle most of these problems as if they were orthogonal. We solved the noise problem, we solved the noise linearity problem, then we solve the bandwidth problem at the end when it is solved, and then we have only a number of solutions that accomplish these conditions. Then we apply biasing techniques for the implementation of the biasing. So we do this in a structured way. So we see a need of characterize all kind of deviations and apply error reduction techniques. And then one of the problems that we saw is that there is always noise. We need to characterize noise, and then we will be doing noise simulations, both in noise simulations, both in transient, so in time domain, and also in AC domain. Then we have to apply biasing techniques to put the active devices in their operating point. So we need to characterize also the DC biasing of our transistors. We will use DC operating point simulation for this. Then some linear techniques or methods, for instance AC do not work in nonlinear devices, so we cannot apply them directly. So we will need to convert the active device models to their small signal circuits. Yeah, that will make possible for us to use AC simulation, for instance, pole zero simulation. Otherwise, we cannot apply these simulation techniques. They are only working with linear systems. So we see the need to transform our circuits to their small signal representation. Yeah, but at some point we will not need to check large signal behavior, and then we start only with DC signal or very low frequency performance, or then we use DC sweeps. We use DC simulation for this. And this low frequency performance assumes that we don't have capacitors, or that the effect of the capacitors or inductors is very, very little in our circuit, so it is just an assumption that works at very low frequencies. At the end of the day, we will need to run large signal dynamic behavior, and that will be with the transient simulator, doing transients in which we can basically take all the performance simulation into consideration with all capacitors and inductors. Okay, so these are the kind of simulations that we will be using to characterize our circuits before we can apply error reduction techniques. Okay, now we'll go to the part of definitions. So there is a number of definitions that we have to be clear before we move forward with the theory. We are going to talk about the source load port requirements. Noise we will handle in a separate lecture, so it is a larger topic, but here we're going to be talking about the operating point. Small signal, static gain, accuracy that it is needed in an amplifier, and a separate lecture we will touch static and dynamic behavior. Now the source and load port requirements, we have that the source and load needs to be very well defined before we design an amplifier, and the reason for that is that if we select the wrong model for the source or for the load, then we will be implementing a wrong amplifier. So it is very important, before even taking into consideration which kind of amplifier topology we are going to implement, we have to be very clear about how does the source and the load look like. And yeah, there are different kind of sources. We have source that behave like a voltage source. That means that it has a series impedance, normally not so large, that it is that is our model for a voltage source. Yeah, that will be connected to the input of the amplifier. Then an alternative is that we can model of source as a current source. Normally we do this modeling when there is a very large impedance. The best model it is a current source. And the load, it is very similar. We can model the output of our amplifier as a voltage source, and then in this case it is expected that our output impedance is very small, or we can model it as a current source. In that case it is expected that the output impedance is very high. Yeah, so we have these four possibilities, and yeah, when we take the type of the amplifier that will be in the middle of these sources, if we assume that my voltage source is voltage and the load source is in the load it is resistive, then the best option for my amplifier is to have infinite input impedance. Input impedance it is here, and zero output impedance. This will be the kind of amplifier that I will want to design. So this is for input voltage and output voltage. We might have input voltage and output current instead, and that is when the load it is very, very small. For instance, that will be this particular case. In my output impedance of my amplifier is very high, I expect to have a very little load, so that all the current flows to the load and not to the source. So I will want to have a high input impedance in my amplifier here, because there is a voltage, and high output impedance at the output, so that all the current flows to the load. We can have the opposite. We can have current at the input and voltage at the output. In that particular case, if we have current at the input, I will want to have this model. If we have current at the input, I want that all the current flows through the amplifier and it doesn't stay in the source. So I will want to have zero input impedance or very low input impedance. If it has voltage as an output, my output impedance, the output of my amplifier should look like this. My output resistance should be very, very low. So I will design for low output resistance. And then we have current, then input impedance will be zero and output impedance will be very, very high, because the output impedance will be like this, trying to go all the current towards the load. Now those are the basic topologies. Then we have that very often we need to drive loads that need both voltage and current, and that means that they have a particular impedance. That is typically the case in radio circuits, radio frequency circuits, that you need to drive, for instance, an antenna that has a very well defined impedance, or a transmission line. In those particular cases, then if we have a voltage at the input and an impedance at the output, we need to match that impedance to have a maximum transfer power. We can have the opposite. At the input, we might have a signal coming from an antenna. Then the input impedance should be a particular impedance that matches, so we have maximum power of transfer of power. At the output, we might have voltage or current. Then I design the output accordingly, either low impedance or very high impedance. And then we have the opposite. We have current at the input and then impedance at the output. Very common in microwave circuits, we have very well defined impedance at the input, very well defined impedance at the output, and then I will have to design both the input and the output at a particular impedance. So these cases will be handled in the radio electronic course, radio integrated frequency circuits design course. We will focus mostly on these ones in this course. Then we have noise. Noise is a random and desired signal that reduce the capacity of the channel, as we saw before from the Shannon capacity theorem. And noise is already present with the incoming signal. So for instance, when we connect an antenna, there is already some noise that will be coming. So the signal to radio will always be lower than infinite, so there is always going to be present. Now, from the design point of view, we don't want to degrade the noise performance. So we will not want to add more noise that it is already present in the system. So it is unavoidable that we add more noise, but we should be very careful not to add substantially more noise than the one present in the system. So noise is a very interesting topic. We have a separate lecture on noise. Now the next thing is the operating point. So as I mentioned before, amplifying devices are nonlinear devices by nature, and then when we make circuits we will have nonlinear curves. To start with, we will need to select a point in which we're going to work in the nonlinear curve, and then for instance we have the input and output here. I will have to decide where to work in this curve. So the operating point or the working point, the operating point, we will call it Q for quiescent point. That will be the point in which the circuit will be working without any information signal coming. So it is just a resting point there. So what do we do with this operating point here is that we will move this point to the origin here. So we move to the origin, so it will look like this. Okay, so we move this point to the origin, and when it is moved to the origin, we can derivate this curve, and then we will have a straight line here. So when we have this, basically this curve moved to the origin and derivated, it becomes a complete linear system. So here it is already a linear system. So there is a linear system, and then we can use mathematical tools that work with linear systems. For instance, we can have the Laplace transform, Fourier transform, we can use superposition, we can use different tools that only work for linear system. We cannot use those ones here. So the linearization of the circuits will allow us to run, for instance, AC simulation. We cannot run an AC simulation here. We need to use it in a linear system. It will allow us to extract the pulse zeros. It will allow us to run small signal noise. So this step is important. We will see an example very soon. Now, how to do the removal of the operating point? So let's check first theoretically how the operating point works. We have a circuit that includes active components. It can be, for instance, one transistor. So we have one MOS transistor here, and the MOS transistor, we can apply voltage at the input. Typically what we have done in previous courses is that we connect this to a VGS voltage source, and then we let some current pass here. Let's put V out here. We let it pass some current here, IDS here, and then we have a voltage that will be here, VDS. This is typically what we do. Then we can do exactly the same to put the transistor in a particular operating point by using the two-port network concept. So we have our transistor, so we embed our transistor here. Okay, so we have our transistor here. We have a two-port network for this, and then we can add to this two-port network these voltage sources. Okay, voltage sources and current sources that put the transistor in this particular operating point. This voltage and this current and this voltage very well defined. by just adding this bias here. So we add this voltage source at the input, we add the current source at the output, voltage source at the output. So we add these voltage sources, and then we need one extra here, current source. What we do here it is that we are adding these voltages and this current here, and placing this transistor in the operating point that we want. And here we can connect our signal V in. Okay, we connect the signal here, and then here we can connect our load. For instance, you have a resistor, we can put our load here. So what is the advantage of doing this? If we have this representation here, we have the transistor, we have a current source, we have voltage here, then we have this voltage source here, and then we have source here, V in, it is AC, and this is also connected here. Okay, what is the advantage of doing this? We have this also here. Now, in this particular case, we implemented the biasing through this resistor here, and then partially also through this gate to source voltage that we don't mention where it comes from, but we expect to have it coming from somewhere. Okay. In this particular case, we have added the biasing circuit here in order to analyze a bias transistor, but most of the time we don't know how the biasing is going to look until we finish the design of the amplifier. So, but placing the expected IDS and the VDS that we want, and the VGS that it is needed to produce this IDS here, it makes very, very easy for us to work with transistors that are not connected to a biasing network. Okay, because we added this, it is because of biasing purposes. So in this case, we just connected this resistor as a load. Now, what happened with this current source here? In the particular case of a MOS transistor, we don't have any DC current that enters other than the leakage currents that might exist, but they are very, very small. So leakage currents are very small, so we delete this one. We really don't need it, so this disappears. So we need only 3 sources to put biasing in our MOS transistor. We need VGS, VDS, and IDS. Okay, so we're going to show this using Cadence. So we have here our circuit. So we have exactly the same circuits that I just showed you. We have a small amplifier in which we have connected power supply, resistor, so we have included this as a biasing network, and then I have placed 394.2 millivolts. So if I run the operating point simulation and annotate the operating points, so we can annotate the operating points from here. DC, annotate DC node voltages and DC operating points. After I run the DC save DC operating point simulation. So then I see that This has to be 394.2 milli. Okay, we run it, and then we see that the current that passing in this transistor is around 100 microamps, and the voltage VDS is around 900 millivolts, also around half of the power supply. Now, look very careful to this. I have exactly the same effect if I place this if I place this voltage source in series to the gate. This voltage source is 0. This is going to be my signal. Okay, so I have VGS 392 millivolts. I have the current source here, it's 100 micro. I have VDS that it is 900 milli, and then I connect the load here. So when I put these voltage sources and the current source here, it guarantees that this transistor will be sinking this current through the drain to the source, and that the voltages at the output here will be 0 volts. In this case it is 500 microvolts, and in this case it's 0 here. So we come back to our presentation. What I am actually doing when I am adding these voltage sources and current sources, it is I am moving the operating points toward the origin. So now my V in is 0 and my V out it is 0. Okay, at the beginning, without moving the operating point, we have that my input voltage it is centered at 394 millis, and the output it is centered at 900 millis. But when I put these voltage sources like this and the current source like this, now I have 0 as my input here and 0 as my output here. So I have effectively removed the operating point. I have moved the operating point towards the origin. And both are basically the same. The transistor it is biased at 100 microvolt. Okay, this is very useful. We have moved the operating point to the origin, and that has been done in a very, very easy way. Then the next part it is that we need to well, we can also extract these curves, and I think that is very useful to do it now. So we are going to run this is sweep. I have already this simulation setup here. Okay. So we're going to be doing here, it is I'm going to sweep the variable V in 2. And that is located, we're going to put it here. V in 2. And I will also call this one V in 2. We run a simulation. Okay, and now let's analyze this simulation setup. We're going to split these ones. Okay. So for this connection, for this schematic here, we have input and output, V in and output V out. So when I plot the curves, we see that I put a marker here. Our operating point is located around 900 millivolts, so it will be somewhere here. I think we can actually do it. A bit smaller. We run. We plot it back, and then put a marker with M, and then change the color to something that we can see better. Okay. Around 900 millivolts. It will be centered here. And the x-axis is the input voltage, is 400, around 400 millivolts. Now, if we take V2, that will be here. That will be for this circuit. That will be for this circuit. I am sweeping the same variable. The same variable is V in 2 here, and the same one that I am sweeping here, it is V in 2 also. So if I take the same one, we see something that it is very interesting and useful. So now this one is centered at 0. Okay, my transfer function have been centered at 0. So we have effectively removed the operating point. So we have this one has been centering in the origin, and it is very nice because I don't have the problem of the operating point being shifting to a particular voltage. So I have removed this, or I have moved the operating point to the origin just by adding the voltage, the gate to source voltage here, drain to source voltage here, and the current that is entering in the transistor here. So we will find practical ways to find these voltages and currents very soon. For now, what is important is that we can move the operating point to the origin by just doing this connection. And it is exactly the same. This resistor is exactly the same as this resistor. And look, here we don't need a power supply. So we really don't need to think about biasing when we are doing like this. Later we will find very nice techniques to create a biasing network. Okay, operating point. The operating point, it is just to find a point in the output curves of the transistor in which we are going to work, and we will see modeling in the next lecture, exactly how to model the transistor. But typically what we will be doing is that checking one point in which we want to work, make sure that this point, it is in a region of operation of the transistor, works as an amplifier, and that region is, we're going to call the saturation region. So in this region, the transistor works as a voltage controlled current source, and we will want to put the transistor somewhere here. And then that will give me what is the VDS that I want to put here. Each of these curves has a particular VGS. There's the VGS that I will put here. and it will produce a particular IDS current. That is the current that I will put here. Yeah? And then when I connect these sources around my transistor, I forget about it because now I remove the operating point. Okay, so we're going to use a lot of these concepts later. Now, last comment here. This is the kind of circuit that we will use until the very last part of our design when everything is working, because then I will focus on how to implement these voltage and current sources. The next definition is the small signal static gain. Yeah, as I mentioned before, we need linearization in order to be able to use linear system mathematical tools like Laplace transform, etc. So we move in a previous step a nonlinear curve to the origin, and then we linearize by differentiating it. And we differentiate this one precisely in the origin. In the next lecture we will do this for a transistor. For now it is just important that you understand that this step is necessary, and then every conclusion that we have in a simulation that it is based on a small signal, it is only valid for very small excursions from the operating point. So that will be valid for very small excursions. So nonlinearities are not assumed here because we have linearized the circuit. We will have to handle nonlinearity with different kinds of simulation techniques. The next definition that it is important is the accuracy. And as mentioned, there will be process variations, devices that do not look the same. They will change the performance. They will depend on how much voltage we apply. They will depend on the temperature variations. So there will be errors that are introduced. And accuracy we defined in the accuracy of our amplifier as the deviation from the nominal gain expressed in percentage. Yeah, so we will be using this formula to define the accuracy of our systems. Now this is important because we need to know from the beginning how much accuracy we will need to implement, because very high accurate amplifiers require very careful considerations and very large loop gain, so that we will pay with complicated designs or complex designs. So we need to be very careful to know exactly how much accuracy do we need. Wrong accuracy specifications will lead to wrong amplifier implementation. Okay, so it's good to know at the beginning how accurate amplifier do we need. So we have a number of topics still to discuss, and the next one will be the static and dynamic behavior. The static behavior we will deal in a separate lecture. It will basically consider how to deal with the low frequency nonlinearities that are always appearing because the nonlinearity of the active devices. Very quickly, if we see our amplifier here, or circuit that we define as an amplifier here, we have an input voltage at the gate, output at the drain. It is going to have a transfer function, as we saw it here. If we derivate the output. This is a function of the output versus the input. If we derivate the output, we will get the gain of the amplifier, the differential gain after differentiation. So I have differentiated here these circuits, and if we take the blue one first, we differentiate the circuit, and we see that the differential gain will be around minus 10.86, and it will only be this value at a very small excursion from the operating point. For any other values, they will change. So we increase the size of this. We see that my operating point will be, I think the biasing was 390 something. I will put a marker here. My operating point will be located here, and then the signal that comes will be amplified with this curve, and then this curve it is non-linear. It produces some error, as we can see. There will be some errors, and the error can be calculated using the equations that we have here. Okay, we can calculate what is the error from the nominal value, and we define the nominal value exactly the one that it is at the operating point. Okay, if we take the other curve, this is centered at the this is for this circuit here, in which we have removed the operating point. We have moved it to the origin. The analysis is much more easier because then we know that it has to be in 0. Okay, then 0 it is there. This will be the nominal gain. It is around minus 10, and then any excursion from the origin, it will create an error. So this is the differential gain error of the amplifier, and we see that the gain of minus 10, it is only happening in the small excursions from the operating point. Then it starts to change the gain very quickly, this particular amplifier. So this is a non-linear behavior, and it is extracted using a DC sweep. Already with this we can predict non-linearities, as we will see in the next lectures. Okay, so we will see later with static behavior linearity at low frequencies. The dynamic behavior is when we consider already our capacitors are high, that start becoming important at higher frequencies because they load the different parts of the amplifier, and then they affect the bandwidth, affect the stability, and affect the slew rate. So what are these ones? For the bandwidth, we will use Laplace transform for most what we are going to do. In Laplace transform, we have that there are poles and zeros. We have the zeros here, and we have the poles here in the denominator. Okay, so any transfer function can be factored to a body normal form in which we have zeros, poles, and we have a constant. And then we can plot these ones as in body diagrams, amplitude and phase. And this is typically what the AC simulator will give us. Again, remember that this is only possible for small signal. Very useful in analog design, we are also going to use pole zeros, in particular for compensation purposes. It is much more easy to use the pole zero than the body diagram. But both are extremely important. Okay, so the very seldom we do small calculations using Fourier representation, also when we are not interested in the transient part. For stability reasons, the transient response of a system, when we take the inverse Laplace transform, will contain some part that is steady and some part that we call it homogeneous. The steady states take the form of the source. If, for instance, it's a sinusoidal or cosine, it will take the same form. And the steady state can be characterized using the Fourier transform. For the homogeneous part, it will only depend on the poles of the transfer function, and that part of the transient takes the following form, in which there are involved some exponentials, and then the roots can be complex numbers. And then it becomes very interesting, because if the real part of the exponential is positive, this will be a signal that grows exponentially. The imaginary part, if we use the Euler theorem, it will give us some sine and cosine response. But the one that we are worried, it is the exponential, if it is positive. If it is negative, it will decrease over time. Okay, so this is something that we have to be careful, because this has to be negative for a stable system, and then an amplifier, we are interested in having a stable system. When we make oscillators, then we will need this to be positive, but most of the time when we are talking about analog design, amplifier design, AK must be negative. So a couple of examples. We have pole plot. We have two poles in the left hand side. When we convert this system to the time domain and we use a step response, typically we characterize this using a step response. That means that we send a step to the system in this time. We will see that the stable system basically do the following thing. So they are exponentials that are decaying until it stabilizes at a particular output voltage or current. We might have complex poles, the system. The complex poles also we characterize using the step input. The output will look something like this. Okay, so the complex poles, we have both the real and imaginary. The real part will do something like this, and the imaginary part will add some ringing at a particular frequency. The system in this case is stable. We have left-hand side poles here. Now what happens if we have the poles in the right-hand side? What we have is that this will be a growing exponential. So we'll do something like this, and that will be oscillating at a particular frequency. And that is an unstable system. So in conclusion, we will be using pole and zero plots to characterize the stability response of our circuits, and then we will do manipulation of the poles, also zeros, in order to guarantee the stability. Slew rate at the output of an amplifier, and then we can load it with some impedance called zeta L. When we apply a step at the input, we will expect that the output also reacts instantaneously, but in practical amplifiers they are limited both by bandwidth and both by the amplitude. So the capacity of an output to respond to a step, a large step, is what we call the slew rate. So at the output, it will change. It will take some time to change from a particular value to the final value, and what we have is that the maximum speed in which this voltage or current can change over time will give you the slew rate. It can be voltage, it can be current, but depending on how we implement the amplifier, in particular the output stage, that will be a limitation of this speed. And then when we're talking about the speed, we are going to talk about bandwidth limitation, because we might limit the bandwidth that can be processed. Think about sinusoidal signal that look very, very quick. It will not be able to be processed by this output unless it is very, very small. If it is very small, same frequency, then it can be processed. So there is both a problem of frequency and amplitude, the slew rate. So this will also be handled in the linearity lecture. We will see the problem of slew rate limitation, how to handle this. Okay, so the slew rate we use as R, and it is voltage or current divided by the time. The next definition that we're going to have today is the two-port ABCD parameters. So very often we deal with our amplifiers as two-port networks. Okay, two-port network. This is a two-port network here. It has an input port and it has an output port here. Yeah, and we use ABCD matrix to define the amplifier capabilities of this two-port network. So how do we define it? We can relate the input voltage and the input current to the outputs. Voltage and output current through the by using these A, B, C, and D complex variables. Yeah, and in principle we can define any circuit. I mean, it can be here any circuit that has resistors, capacitors, inductors. Here inside we can define as a matrix of ABCD parameter matrix. Of particular interest for us is how we define voltage amplifier. So voltage amplifier conceptually we defined as a voltage controlled current source, and that will take amplifying parameter 1 divided by A. Okay, so how do we find this parameter? We make the output output current equal to 0. That means that we don't load the output. Okay, so this will be, the output will be open when it is open, and when that happens, okay, that basically that current will be 0. It will make this part 0, and then we have that the output voltage will be equal to 1 over A V in. Also, the amplifier characteristic will be 1 divided by A. What is important, sometimes it's confusing, this is not the amplification, this is 1 over the amplification. If we do the same exercise for the other types of amplifier, and then we have here the transconductors amplifier. We have an input voltage and an output current. How do we characterize this? In this particular case, what we do is we short circuit the output. Okay, and when we short circuit the output, this becomes 0, and then we have that V in is equal to V E out, or E out divided by V in is going to be equal to 1 over V. So this is what we have here. So that will be our transconductance amplifier. So this is a V voltage amplifier, this is G, and then we have another that amplification that it is the transimpedance amplifier. It looks like this. For the transimpedance amplifier, what we have is that we take the output output current will be equal to 0. Okay, so it is unloaded, totally unloaded amplifier. So it's an open circuit, the outputs, there is no current flowing. And then if this is 0, what we have, it is the E in is equal to CV out, and then we have that V out divided by E in is equal to 1 over C. Okay, so this is what we have here, and for the current multiplier we have this one. This is current, so this will be E, current amplifier. If we plot these ones, or we put as a table here, we have the following alternatives. Voltage amplifier, we have only one parameter, it is available, and it is parameter A. For the transconductance amplifier, we have one parameter, that it is B. For the transimpedance amplifier, we have one parameter, that it is C, and for the current amplification, we have only one parameter, that it is D. And the other parameters will be 0. So what is this interesting? ABCD analysis looks a bit more complicated when we have, for instance, a voltage divider or a series resistor. Looks unnecessary in some cases. However, for very much of the things that we are going to use in this course, it is actually easier to use ABCD parameters. So it is important to have a good background on ABCD parameter. So many of the conclusions that we are going to do during this course come from ABCD parameter analysis. So we will take a look during the exercises and also during the labs how to use the ABCD parameters, because it will be much more helpful than doing a node analysis. So here we have an example of how we use the ABCD parameters to port representation for a bias transistor. So we have the bias transistor that we just have discussed here, and in the next lecture we will see that we can model this bias transistor with a small signal representation with linear components. It will look like this, a very simplified model. And then we can extract all the gains, the voltage gain, transconductance gain, transimpedance gain, and current gain. We're going to do that in the next lecture. And then we can build this matrix of ABCD parameters. So this amplifier can be represented by this matrix. And that will be very useful when we start cascading amplifiers or connecting these two ports in different ways, like differential configuration or parallel configuration. It is very handy because it is very easy to use ABCD matrices for doing calculations instead of using small signal analysis.